This is a special recording for Ken J. Nafziger about my honors capstone project titled Green Chemistry Benchmarking, a tool to analyze chemistry labs at EMU. This presentation was originally given on December 6th, 2014, and so I'm going to give a recording of that. So I'm going to talk about a tool that I've modified to provide information about how green a chemistry lab is, specifically give a number to that lab. And I've been interested in how green our chemistry labs are at EMU, given our focus on sustainability. And so in that light, this tool gives information about minimizing use and generation of hazardous substances, the definition of green chemistry. So I want to talk a little bit about why I've been interested in doing this. This summer I spent a 10-week stint at North Dakota State University where I did research in organic chemistry. This was part of the National Science Foundation REU program. When I was applying for the position, I remember thinking that the title was a bit over the top. Quote, "Want to save the world? Come do research in renewable resources," end quote. Unfortunately, the research wasn't quite as green as advertised. I was performing this synthesis. It's not super important what it is, just that there are reactants on the left-hand side of the equation. Then there are a set of reaction conditions above and below the arrow, and then there are products on the right. However, there's a few small things that are missing, specifically sulfur dioxide and hydrochloric acid, which are actually very important when it comes to green chemistry analysis, but these are often omitted. Sulfur dioxide, of course, is a major component of acid rain, and so that's a really big side reaction, side product. However, often they're largely ignored, and this is really doing us a disadvantage because it's often these small molecules that have the greatest environmental impact, but as written, they're kind of ignored. So I was frustrated about this because my green chemistry research wasn't actually green at all. And the reason I was frustrated is because I've been developing many green chemistry ideas at EMU, largely because they've been introduced right away, starting in general chemistry and then becoming a major focus of organic chemistry. The 12 principles of organic chemistry are listed above. That bullet point is wrong. It should say the 12 principles of organic chemistry. I don't know how that happened. Anyways, they're explained right off the bat, and then in organic chemistry we start to use them in the real world. In early labs, Tara asked us to talk about specific reasons why a certain principle is green. And then later, in labs like 11 and 12, she asked us to talk about the broad themes of green chemistry and tie all our knowledge together. So it's this, along with her focus on research and effective teaching, that means that we're learning the stuff in the classroom. She gives out surveys to see whether we're learning the content or not. The other thing I want to mention is microscale reactions. As the name implies, these reactions don't require very much of a chemical, which exponentially decreases safety concerns along with the environmental impact of that chemical. And many, if not most, labs at EMU are run on the microscale. So this is all great stuff. And we're doing most things right. We just signed the Green Chemistry Commitment this semester, which is wonderful. One of its goals is to track progress. This is also great, except for the fact that the organization, Beyond Benign, doesn't outline how to actually track these changes. So while this sounds great, I'm worried that we're not going to actually implement these ideas because there aren't guidelines about how to do it, and so people largely ignore it. It's not just Beyond Benign who's doing this kind of hand-waving. It's also ACS, the American Chemical Society, which is a massively influential organization in chemistry, that's publishing presentations like this one here, which outlines that a lab should buy less. Great, but as simple as it sounds here, it's much more complicated in a lab setting. And so without real guidelines about how to do that, I think these are going to be largely ignored concepts. Another slide from the same presentation talks about automation and energy conservation and chemical inventory management. All of these things are very complex ideas when they're actually implemented. I've actually been part of a chemical inventory management project last semester, and that turned out to be pretty challenging. So without specific information, I think department chairs, faculty members, or students are likely to kind of let these ideas slide. So that's where Green Star comes in. Green Star is a simple way to determine the relative environmental impact of a chemistry experiment based on the 12 principles. Specifically, Green Star gives a numerical score for each of the 12 principles, and then it gives a total score, which allows us to compare labs and use it as a true benchmark to see if we're making progress by increasing scores. This work is not something that I created myself. Green Star was published in ACS, in an ACS journal this past year in 2014. So first I'm going to explain how the benchmark works in its current form. I'll explain then what modifications I've made, and then I'll give some data about how it applies to EMU's labs. So at the heart of this Green Star assessment is GHS, and I'll get to that in a second. What you're looking at right now is a safety data sheet for acetone. OSHA requires that every manufacturer include a safety data sheet for each purchased chemical. The document outlines the risks associated with a particular chemical, and recently SDSs have changed to implement GHS, which is a standard. What's important though is that it now includes hazard codes shown here. And so Green Star assigns a score to each one of these hazard codes, 1, 2, or 3, where 1 is the best and 3 is the worst. These scores are then entered into an Excel sheet under the appropriate category, health, environment, or accident, where health is about like physical stuff like does a chemical burn you or is ingestion bad. Environment is about like aquatic toxicity, and accident prevention is all about will it explode or catch on fire in the lab. And these scores associated with the hazard codes are used to score each of the 12 principles of green chemistry. So let me give an example of what that looks like for the first principle. That's about waste prevention. So just a quick review, if we look at a chemical, let's say methanol, and the hazard score associated with it, or hazard code associated with it, H301, that gives us a health score of 3. Then for P1, the principle 1, under score 1, waste involves a high hazard to human health, score of 3. That means that we give P1 a score of 1. Which then is entered into the Excel sheet. Finally, all these scores for the 12 principles form what's called the Green Star Area Index, GSAI. This score is found by dividing the area of the green by the area of the red. The green is the score that the principle actually gets based on the experiment, and red is the max score that could be assigned for that principle. The scale is based from 0 to 100 scale, where 100 is the best score. While this benchmark is great as is, I've made some modifications so that it becomes more useful, and so I'm going to go over those right now. First thing I've done is automated it. It was a pain to like follow all these tables and so forth, so now we have some Excel formulas that do that for you. So you put in the GHS hazard code score, and then you get the GSAI. The other thing to consider is that not all principles are considered for a given lab to be factored into the GSAI. For example, the third principle, which is about less hazardous chemical synthesis, is obviously not considered for labs where we aren't actually making anything. We're not synthesizing anything. So that principle needs to be then ignored completely for the GSAI score. In most examples, principles 7 and 8 are ignored, largely because P7 deals with renewable resources, and there just really aren't that many for chemistry. Furthermore, there are no published lists about where to find whether a chemical is renewable or not. So I've just largely ignored that. And P8 is about reducing derivatives. That's something I'm not going to get into here, but it's not done at EMU. The other thing I've done is I've tweaked a few parameters of the analysis itself. The first tweak deals with acids and bases, especially sodium hydroxide and hydrochloric acid, two of the most commonly used acids and bases in lab. At concentrations right out of the bottle, so if you pour 14 molar hydrochloric acid out, that stuff's really dangerous, and so it gets really high hazard scores appropriately. However, for a lot of labs here at EMU, we're using really dilute amounts, like 1 molar or under, and so these hazard scores don't really make sense. So I've added a few rules to make that better, and so at 1 molar or under, all of the hazard scores are decreased by 1 for that particular acid or base. As I mentioned previously, the scale of the reaction also has a profound impact on its safety and environmental impact. The hazard scores given on SDS are generally pretty high because they have to be applicable to all scale reactions. So that's mainly large scale. So if a reaction is small, the appropriate principles are then increased in their score. So those are the category autofill scores. Also, recycling is all about using a product of one reaction as the starting material of the next reaction. And so this cuts down on the P10 degradability score. That's because it's one less thing that needs to break down in the environment. The most significant change I've made has dealt with degradability scores, which I was just talking about. That's P10, principle 10. The authors of the paper didn't give any parameters for scoring this principle, so I looked at SDS, safety data sheets, and it turns out that there's persistence and degradability information already given. For acetone, it's 91%, which means it's readily degradable, so I set up a scoring system based on that, and so now that's included in the GSAI and principal scores. So now that I bored you with the details of how the analysis works, I'm going to give some real data about EMU chemistry labs. For this, I'm going to focus on organic chemistry, largely because I'm most familiar with it and also because Green Star is most applicable to these synthesis labs, a point I'll get to in a minute. I also didn't do rigorous statistical analysis on this data because of the limitations of Green Star. I'm more interested in getting a broad picture of these labs. And so here's what that looks like. So for semester 1 organic chemistry, this is the data. I want to point out a few things. Let's start with the blue bars for labs 4 and 4.1. For lab 4, organic students use dichloromethane, which is not a green solvent. And in the lab write-up, which they turn into Terra, they were asked to compare the procedure with a green procedure that uses dry ice, which is carbon dioxide, instead, which is much greener, except that there's an energy trade-off. You have to use heat to make this work. And so I remember doing this comparison last year, doing a lot of hand waving. I was like, well, replacing this solvent with carbon dioxide is much better for the environment, but we have to increase the energy input. And so that was all great, but here we can see definitively that lab 4.1, which uses carbon dioxide, has a GSAI of 75, while the dichloromethane lab 4 has a score of 50. There's a definite increase. And I think this is where Green Star has its best application. If you have a lab that you're interested in, and you want to see what the environmental impacts are of changing one parameter, you can plug it into this Excel sheet and then see what that actually looks like. I also want to point out that labs under 50 probably could use a look, could could probably use some greening. And so what that means is that you go back to the 12 principles scores and find the ones with the lowest score, and then figure out which chemicals are causing that to happen, and come up with some alternatives based on literature or experiments. In organic chemistry, solvents are usually the worst offenders. So in this example, the average GSAI is above 50, which is really good. Well, it's not really good, but it's above average, and so that means that EMU is doing something right. I do want to point out, though, that Lab 5 with a score of 100 wasn't actually wet chemistry. We weren't in lab. We were merely doing a dry lab. We were doing some molecular modeling using a kit, so we weren't doing any chemistry, any reactions at all. Here's the data for second semester. I want to point out that the GSAI average went up, which is excellent, and this corresponds quite nicely with a greater push toward green chemistry in second semester. I also want to point out scores for each of the 12 principles that we have data for, and point out that P3, Principle 3, and Principle 12 are the lowest scores. Principle 3 has to do with less hazardous chemical synthesis, and P12 has to do with safer chemistry for accident prevention. And so I think these are two very important principles for green chemistry, and so we should probably think about revamping our labs to increase these scores. The scores that are the highest, though, are P9, which is about catalysts. So we're using effective catalysts, and P6 is about energy efficiency, which is also high. That's running reactions at room temperature and atmospheric pressure. So no high temperatures and no high pressures. No high temperatures and pressures, yeah. And so now I want to point out some of the limitations of this. The first has to do with the fact that dangerous chemicals dominate the score. The way it's set up is that high scores for hazard, so you remember that hazard scores are then translated into principal scores and then into the GSAI. So high hazard scores then mean a low principal score and a low GSAI. And it's by a max. So if we have a chemical like furfural, which has really high scores, it doesn't matter that we have furan. That principle will get a very high score. And so that means that disproportionately, dangerous chemicals mean a very low GSAI. And to some extent, this makes sense, because if you have some really dangerous chemical, it'll explode in your face no matter whether you have benign chemicals around or not. So that's an important point to make. The second is that the hazard scores don't necessarily reflect the environmental impact. They're only really thinking about three things. The hazards to aquatic environment, both short-term and long-term, and hazards to ozone layer. There are a lot of different places that chemicals can manifest themselves in the environment that aren't being considered here. These are just three data points that we have a lot of information for. I also want to point out that safety data sheets also don't have a lot more information than that. If they do have categories, they often don't have any data for them. And of course, that's what I'm going to talk about next. There's a lot of data missing, and so that influences scores quite a bit. Finally, it'd be useful to include costs of purchasing, but especially of disposal, to this assessment. It turns out that hazardous waste is very expensive to dispose of, and so labs are always looking for ways to cut down on the amount of waste that's generated. And because of the correlation between high hazard and high cost, this cost might be an additional parameter to include to encourage labs, encourage students and professors to use less of these chemicals. So the overall message I get from this is that many of the reasons that benchmarks like this haven't been developed, this is actually the only one I could find after quite a rigorous search, is due to the fact that green chemistry is very individualized. It requires creative and unique solutions for a broad range of problems, so a one-size-fits-all approach like this one does have its serious drawbacks. And so now I want to mention a few ideas for the future. It's already published data, so we really can't do anything there, but it would be cool to create a web app, adding one extra layer of automation. Instead of having to put in hazard scores, you could just put in the hazard codes and get the GSAI right from that, and also put in the other parameters that I mentioned. And this would give us the GSAI score. It'd be really cool to include something like this on the EMU website somewhere, so that chemists and students from around the country could access it and learn something more about their labs, see how green they are. That's really what I have to say about this presentation. I'd be happy for any questions you have.